Welcome to Learning Outcome 1, where we get to grips with measures of spread. By the end, you'll be able to describe not just where a dataset sits, but how spread out its values really are. Whenever you've got a pile of numbers, statistics helps you boil them down so you can compare and decide. There are really two questions worth asking about any dataset. Where's the center, and how spread out are the values? Say two football teams. Both average 2 goals a game. One might score exactly 2 nearly every week, while the other swings between 0 and 5. Same average, completely different story. And that's why spread matters just as much as the average. Let's line up the 3 averages. The mean is the one most people know. Add everything up and divide by how many values you've got. Written x bar equals the sum of x divided by n. The median is the middle value once you've put the data in order, and if there's an even number, you average the middle too. The mode is simply the value that crops up most often. Take 5 test scores of 3, 7, 7, 8, and 10. The mean is 7, the median is 7, and the mode is 7 as well. Now, the spread. The range is the crudest, highest minus lowest, quick to work out, but one freak value throws it right off. The interquartile range looks only at the middle 50% of the data, so it shrugs off outliers. And the standard deviation measures the typical distance of the values from the mean, which is why it's the workhorse of statistics. We'll build up to all 3 across this outcome. Let's walk one through. A shop records its daily sales over 7 days, 8, 5, 9, 12, 5, 7, and 10 items. First, put them in order. 5, 5, 7, 8, 9, 10, 12. The mean is all 7 added, that's 56, divided by 7, which gives 8 items. The median is the 4th value, the one bang in the middle of 7, and that's 8 as well. The mode is 5, because it's the only value that appears twice. And the range is 12 minus 5, which is 7 items. 4 little numbers, and already we know a great deal about those sales. Once a data set gets big, listing every single value is a pain, so we bundle them into class intervals. Things like 0 to 10 or 10 to 20. Grouping makes the data far easier to read, but there's a trade-off. We lose the exact individual values. To get an average back out, we treat every value in a class as if it sat at the midpoint. For a 20 to 30 class, the midpoint is 25, halfway between the boundaries. Because we lean on those midpoints, any average we get is an estimate, not the exact figure. Here's a real one. The time 40 customers spent browsing a website, sorted into 10-minute classes. 4 people browsed for under 10 minutes, 9 for 10 to 20, 13 for 20 to 30, 10 for 30 to 40, and 4 for 40 to 50. The midpoints we'll use are 5, 15, 25, 35, and 45 minutes. Notice the frequencies add up to 40, which is our total number of customers. We'll put this table to work on the next slide. To estimate the mean from grouped data, we multiply each midpoint by its frequency, giving an F times X for every class. 5 times 4 is 20, 15 times 9 is 135, 25 times 13 is 325, and so on down the classes. Add that whole column, and the sum of Fx comes to 1010. Divide by the total frequency, 40, and you get 1010 divided by 40, which is 25.25 minutes. So on average, customers browsed for a shade over 25 minutes. Remembering it's an estimate because we use the midpoints. 2 more things we can read off grouped data. The modal class is just the class with the highest frequency. And here, that's 20 to 30 minutes, with 13 customers. The median class is the one holding the middle value. With 40 customers, the middle sits between the 20th and 21st. Building running totals gives 4, then 13, up to 20 minutes, then 26, up to 30. Both the 20th and 21st values land inside that 20 to 30 class, so that's our median class too. To pin the median down more precisely, we'd use a cumulative frequency diagram, which is coming up later. Standard deviation sounds intimidating, but the idea is simple. It measures the typical distance of your values from the mean. A small standard deviation means the data is huddled tightly around the mean, nice and consistent. A large one means the values are spread out and variable. Unlike the range, it uses every single value, so one odd result doesn't dominate it the way it dominates the range. You'll find it everywhere, from quality control on a production line to exam grading to measuring risk in finance. Let's lay out the method step by step. Step 1, find the mean, x bar. Step 2, find each value's deviation from the mean. That's x minus x bar. Step 3, square each deviation, x minus x bar all squared, which conveniently kills off the negative signs. Step 4, average those squared deviations, and that average is called the variance. The sum of x minus x bar all squared, divided by n. Step 5, take the square root of the variance, and that's your standard deviation. The square root is what brings you back to the original units. Time to put numbers in. Take the data 4, 6, 8, 10, 12, 14 and 16, so n is 7. The mean is 70 divided by 7, which is 10. Now the deviations from 10 are minus 6, minus 4, minus 2, 0, 2, 4 and 6. Square each and add them up, and the sum of x minus x bar all squared comes to 112. The variance is 112 divided by 7, which is 16. And the standard deviation is the square root of 16, which is 4. So on average, these values sit 4 units from the mean. Notice too that the deviations themselves sum to 0, which is exactly why we square them first. Here's where standard deviation earns its keep. 2 machines fill 500-gram bags, and both average 500 grams exactly, so the mean alone can't separate them. But machine A has a standard deviation of 3 grams, while machine B's is 11 grams. Machine A's bags nearly all land within 500 plus or minus 3 grams, tight and reliable. Machine B swings far wider, 500 plus or minus 11, so many more bags come out under or overfilled. For quality control, you'd pick machine A every time. And that decision comes entirely from the spread, not the average. A couple of tips on reading a standard deviation. Because it's in the same units as the data, grams, minutes, or pounds, you can interpret it directly, but always weigh it against the mean. A standard deviation of 5 is huge when the mean is 10, yet tiny when the mean is 1,000. That's what the coefficient of variation captures, the standard deviation divided by the mean, letting you compare spread across datasets of very different sizes. Broadly, a larger standard deviation flags more risk or inconsistency, and a smaller one signals stability. Cumulative frequency is just a running total of the frequencies as you climb up through the classes. We plot that running total against the upper boundary of each class, so against 10, 20, 30, and so on. Join those points with a smooth curve, and you get what's called an ogive, a cumulative frequency curve. The lovely thing about the ogive is that you can read the median, the quartiles, and in fact, any percentile straight off it. Let's build one. Suppose 60 deliveries are timed. 3 take up to 10 minutes, 8 up to 20, 15 up to 30, 16 up to 40, 12 up to 50, and 6 up to 60. The cumulative frequencies stack up like this: 3, then 11, then 26, then 42, then 54, and finally 60. With 60 values, the median sits at the 30th, the lower quartile at the 15th, and the upper quartile at the 45th. Those positions are what we'll hunt for on the curve. Reading the median off the ogive is genuinely satisfying. With 60 values, the median is at a cumulative frequency of 30. That's n divided by 2. So you go to 30 on the vertical axis, draw across until you hit the curve, then drop straight down to the value axis. For our delivery data, that gives an estimated median of about 33 minutes. The same trick finds the quartiles. Read across at 15 for the lower quartile and 45 for the upper. A table of totals suddenly becomes readable statistics. Let's be precise about quartiles. They chop the ordered data into 4 equal parts. The lower quartile, Q1, sits a quarter of the way through, at a cumulative frequency of n divided by 4. The median, Q2, is halfway, at n divided by 2. And the upper quartile, Q3, is 3/4 of the way, at 3an divided by 4. The interquartile range is Q3 minus Q1, the span of the middle 50% of your values. Because it throws away the extreme quarter at each end, outliers simply can't distort it. Back to our 60 deliveries. The lower quartile sits at a cumulative frequency of 15. Read across and down, and you get a Q1 of about 22 minutes. The upper quartile is at 45, which gives a Q3 of about 44 minutes. So the interquartile range is 44 minus 22, which is 22 minutes. In plain terms, the middle half of all deliveries spans about 22 minutes. If that was small, compared with the full range, you'd know most deliveries cluster tightly around the center. A box plot is a neat way to picture all of this at once, using the 5-number summary: minimum, lower quartile, median, upper quartile, and maximum. For our deliveries, that's 12, 24, 31, 38, and 58 minutes. The box itself spans the interquartile range, with a line inside marking the median, and the whiskers stretch out to the smallest and largest values. Notice the long right whisker here, reaching all the way to 58. That's a handful of slow deliveries pulling the maximum up. Box plots really shine when you want to compare the spread of 2 or more groups side by side. So, which measure of spread should you reach for? The range is quick, but easily wrecked by a single unusual value. The interquartile range is resistant to outliers, which makes it ideal for skewed data or data with extremes. The standard deviation uses every value, so it's best for roughly symmetric data and for any deeper analysis. Think about house prices. A few multi-million-pound properties drag the mean and range right up, so the median and interquartile range give a fairer picture. There's no single best measure. You match it to the shape of your data. Let's gather it all up. Central tendency, the mean, median, and mode, tells you where the center is, while spread, the range, interquartile range, and standard deviation tells you how variable the data is. For grouped data, we lean on class midpoints, so the estimated mean, the sum of fx divided by the sum of f, and the modal and median classes are all estimates. Standard deviation is the typical distance from the mean. Square the deviations, average them for the variance, then take the square root. The cumulative frequency ogive lets you read off the median at n over 2, the quartiles at n over 4 and 3n over 4, and the interquartile range as Q3 minus Q1. And remember, the median and interquartile range shrug off outliers, so they suit skewed data, while the mean and standard deviation suit symmetric data. That brings Learning Outcome 1 to a close. You can now summarize a data set by its center, and just as importantly, by its spread. If you'd like to go deeper, the reading list points you to friendly starting points, like Rowntree's Statistics Without Tears, alongside a more thorough course text from Crawshaw and Chambers. For real data to practice on, the Office for National Statistics website is a goldmine, and Corbett Maths has plenty of worked video examples on standard deviation and quartiles. Have a browse, then try applying these measures to a data set of your own before you move on.